Hi everybody, we're continuing chapter 6. Hopefully we'll finish it today and maybe jump into chapter 7, we'll see. This is a little bit from last time. We were talking about the SN2 reaction, which is the topic of chapter 6 for the most part. We were talking about nucleophiles and the kind of the different types of nucleophiles and the effect of various things on nucleophilicity and what makes good nucleophiles good and bad. We ended last time on the effect of protic and aprotic solvents. Protic and aprotic solvents, which are just different kinds of solvents, and there's a huge solvent effect in SN2 reactions, and that's what we're kind of getting to. And I gave you the preview that the aprotic solvents are actually really good for SN2. And what was a protic versus aprotic? The two kinds of solvents. Polar protic, or what you're maybe most familiar with, maybe in your common life, if you think about things like water, which has a classic polar protic solvent. They're solvents that have hydrogen bond donors on them, like OHs and NHs and stuff like that. Not CHs, because those aren't acidic, and these are moderately acidic. The protons on water and methanol and ethanol, those are considered acidic protons, and they can be removed, they can hydrogen bond and things like that. So when we talk about polar protic solvents, polar due to the electronegative oxygens, and protic due to them being hydrogen bond donors. Okay, and then we have polar aprotic solvents, which are polar by nature of having a dipole, like a C double bond O or something like that. But they're aprotic in that they lack an H bond donor. Alright, this is all from last time. Typical examples are like acetone. Acetone has a ketone functional group. Acetonitrile has a nitrile functional group. Of course, that has a delta minus and delta plus, so it's very polar. Delta negative, delta plus, delta negative, delta plus. So they are polar functional groups and polar solvents. The fact that these are delta negative, delta plus will actually, dictate the reactivity of these. We're not using them as reactive reagents right now, but in later chapters, we're going to talk about the reactivity of ketones and nitriles. Might be organic too, actually. But yeah, these are totally reactive if, nucleophiles, for example, can attack them. But that's not this chapter. Another important one is called DMF, dimethylformamide. DMF, dimethylformamide. It's an amide, and being an amide, that's due to the amide functional group, C double bond O N. Dimethyl, in this case, refers to the two methyls on nitrogen. Sometimes it's called N, N dimethylformamide. What's the NN mean? That means you have two methyls on the nitrogen. There's only one nitrogen. NN refers to the same nitrogen. NN dimethylformamide, or DMF. Memorizing the abbreviation is probably a good idea. Just, you should have a little catalog of good polar aprotic solvents for SN2 reactions, and DMF is a pretty easy one to remember. And then we have dimethyl sulfoxide, DMSO. Sulfoxide kind of looks like a ketone, except it's based on sulfur. So dimethyl sulfoxide and acetone are kind of similar in structure, aside from that sulfur. And this is a really, really good polar aprotic solvent for SN2 reactions also. Another one we will see from time to time is nitromethane. Nitro refers to that N double bond O, single bond O thing. So nitro is that, and then methane, it refers to the methyl group. And so nitromethane is another polar aprotic solvent that we see sometimes. And that's what a nitro functional group is, right? NO2. Okay, and then as we were concluding last time, we were asking kind of like, why does it matter? Why are polar protic and polar aprotic important at all to consider? And yeah, the polar Protic are slower due to that hydrogen bonding. We'll see that in a second. I'll draw it out. And then I was just showing like an example from last time of like an example of how a polar aprotic solvent, the good ones, might work in an SN2 reaction. And it just showed like potassium cyanide SN2 reaction, potassium cyanide SN2 with a secondary bromide to the nitrile. And then DMF or DMSO are really good solvents that speed it up. Okay, so how fast do polar aprotic solvents speed up reactions? So we're still on 8, which is on the nucleophile. Nuke. D is on polar protic and polar aprotic. Solvents, polar protic and polar aprotic solvents. So let's just consider a reaction. Methyl iodide, riodomethane, reacting with NaCl. Nice, simple SN2 reaction, right? Delta minus, delta plus. Mechanism is very simple. Chloride attacks, kicks off the iodide, right? To make chloromethane and sodium iodide. Okay, so let's consider a couple solvents for this. And we'll talk about the solvent names and the type of solvent and the, I'm going to say the relative rate, which means it has to be relative to something, and it'll be relative to the first example. And first example is methanol, or CH3OH, right? CH3OH, MEOH, same thing. Is this protic or aprotic? Well, you got the proton there on the oxygen. Of course, you also have the CH3, but those protons don't count for this for the sake of being protic and aprotic. It's really that OH, right? So it is a protic. And the relative rate is 1. So yeah, the reaction goes. It's going to be 1. All right. This one. Is an amide, and it kind of looks like dimethyl formamide. Remember DMF? Except the DMF, it's 2 CH3s there. Anyway, this is also protic, but these protons are a little less acidic, and the rate is a little faster, 12.5. Okay, so it's a little bit faster. Its relative rate's a little faster. And what about this one? So now it's like a single methyl on formamide. Single methyl. So it's kind of similar to the top one, but we have one less proton there. And what's the relative rate of this one? Well, it's actually faster. It's 45.3. Okay. So yeah, the effect of like kind of losing protons, and if they're slightly less acidic protons, that actually speeds up the rate. So what about now, what's that other one, 3 letters, DMF. We call this, what is it, protic or aprotic? Because yeah, you see a proton there, you see some protons there, but those are not hydrogen bonding protons. They're not hydrogen bond donor groups. So this is actually aprotic. Okay. And any guesses on the speed? Is it going to be faster or slower? Well, I already told you. I said that aprotic are faster. The question is it just a little bit faster? I don't know, it's like 100 or 200. I don't know. What do you think? So the relative rate of DMF, which is called DMF, right? Dimethyl formamide, is, ready for it? It's 1.2 million times faster. So that's a significant rate increase by just getting rid of the hydrogen bond donating groups. It's a polar aprotic solvent, and the rate is just ridiculous. Okay, so why is that? And why I mean, the question would be, why are protic solvents a little slower, or in this case a ton slower, and the aprotic solvents faster? Okay, so, and I already gave you the answer also, but we'll draw it out now. So in the polar protic solvents, there's extensive hydrogen bonding, H bonding around the nucleophile. Extensive H bonding around the nucleophile, and that just destroys the reactivity. So what's our nucleophile up top? It's chloride, right? Cl minus. All right, so Cl. Let's just imagine the Protic case, the slow one. There's a nice chloride. It wants to go attack and be a nucleophile. When we have a solvent like methanol around, there's a bunch of methanol around, and those are all delta positive. All the H's are delta positive, and you have the Cl minus, and there's this interaction, right? It's interacting with all those H's, those hydrogen bond donating groups from the alcohols, right? There's tons of those little interactions, and if you're the chloride trying to go react with iodomethane, do you like that or not? You know, is that going to prevent you from reacting? If you're the little chloride atom and you're trying to go attack, go react, be a nucleophile, if you're completely blanketed with solvent, what's the likelihood that you're going to be able to sneak out of the solvent cage and go react? Yeah, you can. It's just it's slow. It's slowed down, right? What about the sodium? Is the sodium doing anything? Let's draw the sodium, Na+, right? Because there is sodium around. Is it reacting with anything? Because you still got sodium too. You have Na+, you have Cl minus. Charge of sodium is plus. What atoms are, if the H's are delta positive, they're all delta positive, right? There's a proton. And the oxygens are delta negative. So those are like delta positive, delta negative. All the oxygens are delta negative. Well, they're interacting with the sodium, right? Oxygen, oxygen. Right? Etc. Oxygen, H, blah, blah, blah. Okay. Now, which interaction really slows down the reactivity? The interaction of the chloride or the interaction of the sodium? Because we know the sodium is a spectator, so it doesn't do anything, right? It's not the nucleophile. That's a nucleophile. So, yeah, they're both happening, but which one really affects the reactivity? That one, right? That one will really slow it down because they can't go react, all right? Now let's consider polar aprotic. So this is the polar protic, like methanol. There's polar protic. I'm going to jump over here and then I'll zoom out when I'm all done. Polar aprotic. Now, okay, polar protic, polar aprotic. Like DMF. Alright, so now we have the chloride, Cl minus, the good nucleophile that we want to use. Well, with a polar aprotic solvent, we don't have all those hydrogen bond donating protons around, right? There's no protons that are acidic that could react or interact with Cl. So yeah, there's a little bit of very little interaction. Let's draw that a little nicer. We have DMF. There's dimethyl formamide, right? There's a little bit of a partial delta positive on the carbon, right? There's a little bit of a delta positive on the carbon. Delta positive on the carbon, and then you have delta negative on the oxygen and delta negative on the nitrogen. Very little, right? But also the DMF structure is, you know, there's the big CH3 groups kind of prevent any interaction with that carbon. All right, so let's draw Cl minus hanging out. And yeah, there's these very minuscule interactions with the delta positive carbon. The chloride is delta negative, maybe the carbons are delta positive, but that's a minor interaction. Okay, so that anion is not really shielded or blanketed the way that chloride was. Chloride was totally blocked from reactivity. Here it's not really. But what about the sodium? Na+. Well, the sodium is actually getting interactions with, like, the C double bond O. Right? Okay, so now we're just kind of focusing on the sodium. Yeah, we have all these little interactions. Dot, 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 dot. You can probably draw this a little nicer. Okay, so yeah, there's lots of little interactions between the sodium plus and all the little delta negative oxygens, right? They're all delta negative. Yeah. Okay, but the chloride, the thing that actually matters, that's actually going to be the nucleophile, it doesn't really have any problems, right? So it's not blocked, and it's able to go do its thing and go react with the electrophile, the substrate. Okay, so net effect, when you look at both of these, polar protic solvents, you have extensive hydrogen bonding around the nucleophile, can't react, won't go do its stuff. Polar protic, yeah, you have little minor interactions with like delta positive carbon, but it's not as extensive as this, and that chloride is free to go be a nucleophile. But what about the sodium? Well, who cares about the sodium? It's a counterion. It's not doing anything of substance in the reaction. This is the actual substantive reagent, the nucleophile, right? Okay, and so what's the net effect? Go back up to the table. Look at that, DMF reacts 1.2 million times faster than methanol. It is all about the fact that it's not a hydrogen bond donating solvent. Okay? So this is the overall scheme we just kind of presented. You can go back through it if you need more want to look at it one more time. Alright, so one more quick example of the polar aprotic stuff. 8 and D. So polar aprotic versus aprotic. Real quickly though, I'm not going to spend much time on this one. Bromobutane, 1 bromobutane. Sodium azide, which we've talked about before. N double bond N, negative, positive, negative, to make azidobutane. N double bond N, and then NABR is the byproduct, right? Okay, and then we vary the solvent. And just as a quick example, solvent, relative rate. Methanol was 1. Water, surprisingly to me a little bit, is that it's actually a little bit faster. It doesn't totally make sense. DMSO, which is one of the polar aprotic solvents, is 1300, so a bit faster, huh? DMF is 2800. 2800, so not as substantially faster as the other reaction. Surprising, it's not 1.2 million times faster. There's some differences here, though. It's primary versus methyl. In this case, the winner was acetonitrile, which is one of the other ones, 5000. Okay. So, and these are all polar aprotic. Okay, and so, you know, without nitpicking which is the best, you know, if I ask you in the future, I ask, you know, what's your favorite SN2 solvent, or yeah, favorite polar aprotic solvent or whatever. And I don't know, DMF, DMSO, those are pretty good. Acetonitrile is pretty good, maybe harder to remember. If you just are good at memorizing like 3-letter abbreviations, DMF and DMSO are pretty good to memorize. Okay? Acetone's also a good one too. It's not on this chart. Okay, we're done with that. The Protic, aprotic stuff. This one's totally obvious. Sterically hindered, because we're talking about nucleophiles still, and when we talked about the solvents, that was kind of the effect of the solvents on nucleophilicity. You can almost think of this as being a different topic, but our textbook puts it with the topic of nucleophiles. But now we're back to other nucleophile issues. Sterically hindered nucleophiles. Sterically hindered nucleophiles are, do you think they're going to be faster or slower? It's hindered, it's like blocked by something. Do you think it's going to be faster or slower? And you probably guessed right, that is slower. Hindered would make it go slower. So if I have two identical nucleophile, or two identical functional groups that are nucleophiles, so this is isopropoxide. What are they called? Alkoxides, right? Alkoxides. Alkoxides refers to carbon-oxygen negative. Carbon-oxygen negative. They're called alkoxides. Or this one I called it isopropoxide because it's isopropyl alkoxide. Isopropoxide. Okay, so yeah, this is an easy reaction. SN2, kick off the bromide, and what do you get? 4-carbon attachment, make an ether. Alright. And then what if I compare that with methoxide? Yeah, and do the same thing. Okay, it's different alkoxide, but they're, you know, not that different. To make the methyl ether. Alright, nothing really substantially different. Two different alkoxides. Which is the fast reaction, which is the slow reaction? We haven't really addressed this yet, but it totally makes sense that maybe the fast one would be the sterically less hindered one, with the methyl without those extra methyls. So this is the fast one, slow. Totally makes sense, right? Due to the steric hindrance of the top one. Okay. Alright, so we're cool with that. Sterically hindered nucleophiles are slower. This is another little interesting tidbit that you may have thought about, but we haven't really discussed yet in the lecture. This is F. F is that nucleophilic substitution can be reversible. Nucleophilic substitution can be reversible. Nucleophilic substitution can be reversible. Now, what do we mean by that? It's interesting that if I take this optically active single enantiomer 2-iodopentane, optically pure. What did optically pure mean? Optically pure means that it well, it rotates light kind of at the maximal level for this substance. You know, if it was a mixture of enantiomers, like if it was racemic, it would be racemic would be no optical rotation or optically inactive. Optically pure basically means, oh yeah, it's a single enantiomer. Single enantiomer. That's all it means. Single enant. Single enantiomer. What we know that iodide is a what kind of group is that? It's a good leaving group, right? But it's interesting that it's also a good nucleophile. It's a good leaving group and a good nucleophile. That's weird, right? Maybe you've thought about that before, but it's definitely true. Yeah, it's a good nucleophile and a good leaving group. And so if I take this stuff, and right now it's a single enantiomer, and I expose it to sodium iodide, DMF, good SN2 solvent, polar rate Protic solvent, what's going to happen? Is it going to stay optically pure? Well, you can imagine that once you take this, this might react, and we'll say assume excess. We have a lot of this, a lot of sodium iodide around, right? It's going to kick it off and make it go dash dash dash. So enantiomer inversion, right? And it's going to keep doing that back and forth, back and forth, and back and forth until it's not going to be optically pure anymore. It's going to be a mixture of enantiomers. It's going to be racemic, right? So if you do this and you have this optically pure stuff and you react it with excess sodium iodide, you will very quickly have a mixture, a 50-50 mixture of enantiomers, right? 50-50. Eventually. It could be, I don't know the exact rate. It might be a kind of quick thing. What's it called if it's a 50-50 mixture? It's called racemic. And if we consider the optics of that, this is optically pure, this is optically inactive. So it was rotating light. Now it's not rotating light anymore because you have a mixture of enantiomers. Okay, and that's due to iodide being a good leaving group and also good nucleophile. Iodide, good leaving group and good nucleophile. Okay, so it's sort of reversible, right? So this, you know, this can react, and then it'll just keep reacting and reacting and reacting until eventually you basically just get stuck with a 50-50 mixture. Okay. Okay, so that makes sense. Let's mention something else now. If I have 1-iodobutane, I don't know if you remember the bond dissociation energies, probably not, of like a carbon iodide bond versus a carbon chloride bond. Carbon iodide versus carbon chloride, bond dissociation energies. Do you remember which one is the stronger bond? Well, iodine is lower on the periodic table, so it's got the mismatched orbital problem. Chloride's higher on the periodic table, so it's closer to carbon on the periodic table. But interestingly, well actually not too interestingly, I think it's pretty obvious, iodide's a weaker bond. Okay, those are kilocalories per mole. Okay, Yeah, the iodide's kind of a weak bond. And so if I react with lithium chloride, this should be a nice favored equilibrium that goes to the right. And I'm going to throw in a polar aprotic solvent like acetone. So yeah, this is my point is that this is actually this is an equilibrium, right? Where the chloride can kick it off, and then the iodide can kick off the chloride, right? So it's like, you know, which direction is this equilibrium favored? It is an equilibrium because they're both nucleophiles and they're both leaving groups. This is favored to the right. And then you would get some lithium iodide, right? And that's why is it favored to the right? Well, that's due to the you know, this is actually a happier molecule. This is a more favorable molecule due to the higher bond strength. Okay. All right. So it's actually easy to go from an iodide to a chloride. All right. And why is that? It's due to the product stability. The chloride actually has it's more stable. Less stable. And whenever you have a more stable and a less stable product, the equilibrium is usually shifted towards the more stable product. Okay. All right. So it's exothermic too. Exothermic. If you do the calculation, it'll be a delta G is negative. I don't have the number. Okay. But you can actually calculate delta H and delta G, and it'll be a negative number. Okay. Now this is where there's something interesting that happens. Because if I go from butyl or chlorobutane, and I'm actually going to have to change this from a lithium salt to a sodium salt. There's something special about the lithium versus sodium here. And I'm going to react it in acetone, so I'll leave the equilibrium arrow out. I'm going to leave the equilibrium arrow out temporarily. And then I'd form iodide, right? And I'd form NaCl. The question is, which direction is this equilibrium? Based on what we just explained, you would think that this would be a left-favored equilibrium because chloride is actually more stable, right? Chloride's more stable, that's less stable. So what could possibly be the explanation for me to say, oh no, it actually does go to the right? That's weird. That totally contradicts everything I just said, right? This actually is a forward-leaning reaction, going from a more stable thing to a less stable thing. How could that possibly be? It's so weird. Okay, and the reason is that in the case of sodium iodide in acetone, this is soluble. So this is a soluble reagent. It's actually, and it's soluble, it's actually reactive. This actually dissolves in acetone. And for whatever reason, sodium chloride does not like to be dissolved in acetone. So this is insoluble. It's insoluble. And what happens when something forms that's insoluble? It crashes out of solution. It forms a solid. And then what's the net effect? If I have A plus B going to C plus D, and then I remove D, D gets lost because it gets insolubilized. Well, that'll force the equilibrium to the right, regardless of the fact that these are actually, you know, a more stable thing and a less stable thing. So and I'm not like violating thermodynamics. If you do all the calculations, this will go to the right because there's more to an equilibrium than like these two molecules. So the differential solubility of this versus that is important. And also this happens to be very, very stable. Sodium chloride is a very, very stable thing. So even though this is less stable, this is more stable. And the net effect is that it goes to the right. So this is a very cool little trick to actually convert a chloride to an iodide. And you have to use acetone. And this is a case where the counterion is important. Sodium actually is crucial to this strategy. Lithium, pretty sure that both of these are actually soluble in acetone, so they're not really involved in the equilibrium. In the top reaction, what really matters is the fact that it's just going from iodide to chloride. Okay, so that's very cool. Yeah, and so in summary, there we have A plus B. Whenever you got A plus B going to C plus D, what are the ways to shift the equilibrium to the right? You could either increase one of these guys or decrease one of these guys. And in this case, what's happening is we're decreasing D by it falling out of solution. Okay, this is actually an example of a named reaction. A named reaction by named. Somebody came up with it and they slapped their name on it. This name is called this reaction is named the Finkelstein reaction. Finkelstein reaction. It was named after Hans Finkelstein. Hans Finkelstein. And this was discovered in 1910. So it's a pretty old reaction. A lot of organic chemistry is really old. So anyway, you actually now know a named reaction named after Hans Finkelstein from 1910. Okay, so a little more on SN2. We are done with the nucleophile, which was number 8. Now we're on to what's the one thing we haven't really talked about? SN2 reactivity, the substrate. Now the substrate is actually a pretty straightforward section. There's not that much to talk about. Relatively easy. We can talk about the basic kinds of substrates. Methyl, is it a fast substrate or a slow substrate? Methyl, let's get CH3. CH3 bromide, CH3 iodide. It's actually fast because there's nothing around it, right? So that's going to be the fast one, and then we got primary, which is like that. It's going to be next in line in terms of speed. Then we have secondary. Something like that. And then tertiary is basically impossible. So the rate of tertiary SN2 is like basically 0. It just doesn't happen. We can't observe it. So this is a little bit of an understatement. You should just assume that tertiary SN2 does not happen. Never. Okay. But we do have, what we will see in the next chapter is SN1 reactions do happen. Yes. SN1 happen on tertiary. Okay? And we'll talk about SN1 shortly in the next chapter. Relative rates of these different substrates. So we're just going to use a simple nucleophile like azide. Negative plus negative. Remember that. Azide. Because we have like lone pair, lone pair, lone pair, lone pair. Whatever. Just fit in those lone pairs. The middle nitrogen does not have any lone pairs. And then if I consider methyl bromide versus ethyl bromide versus isopropyl bromide, so that's going to be methyl primary secondary, versus tert-butyl bromide, which is tertiary. And I consider what are the products? What are the products? So we have methyl N3, methyl azide, versus ethyl azide, versus isopropyl azide, versus tert-butyl azide. And of course there's Br minus, Br minus, Br minus, Br minus. And the relative rate of those reactions. Methyl is 18,560. 18,560, so relatively fast. 18560. Ethyl is 128, and then the secondary, which is primary, right? Primary, and then secondary is 1. So everything's kind of based on secondary, because secondary is the fastest SN2 reaction. This doesn't really apply, so we just say Na. We can't measure it for tertiary. Tertiary is just not a viable SN2 reaction. Okay. But it will. There will be SN1 reactions of tertiary next chapter, which is just a different mechanism, a different style of reactivity that does undergo on tertiary. Okay. So why do we see these rates? Why do we see the rates above? That's pretty obvious. It's all steric hindrance, right? Steric hindrance. And as you get more and more sterically hindered, it's faster. It's slower, right? Or you could say if you have less and less steric hindrance, it's faster. So this is like kind of sterically hindered with a secondary. And then primary is a little less sterically hindered because you got rid of one of the things, and now it's faster. And then you get rid of that other CH3, and now it's methyl, and it's like super fast. Okay? Very nice. There's also a figure, I think, 6.8 in the book that talks about this and kind of shows the steric hindrance a little bit. One more example along the same lines. Lastly, I think this might be the last topic in this chapter. Branching next to the substitution where the leaving group is. Substitution. Diminishes reactivity. Diminishes. Branching next to the substitution diminishes reactivity. Okay, so as an example, let's consider simple nucleophile cyanide, CN minus. And is that a good SN2 reaction? Use some DMF or something. Yeah, totally. It'll work. That's a great SN2 reaction. Because is this primary, secondary, or tertiary? Primary, secondary, or tertiary? That looks very primary, right? The carbon with the leaving group is connected to one carbon, so that's primary. And yeah, no problems with this reaction. Attack, kick off. Now you get the nitrile, get some Br minus. Yeah, nice fast reaction. Let's do the same thing now with the same thing, same substrate with a methyl there. And fast, slow, different, not different. What kind of substrate is this? Is this primary, secondary, tertiary? Well, it's still primary. It's still primary. Now we got an extra methyl next door, but we're still primary. And to give yourself good luck in the SN2, we'll do primary, or polar aprotic solvent, DMF. And that would be the product, and you get Br minus. And then the question is one of these faster or one of these slower, or is there no difference at all? Because they're both primary, you might think, oh, no difference, both primary, right? So this is much faster, much slower. Much faster, much slower. The effect of the methyl group really diminishes the reactivity. So when this would go in and attack, there's a lot of steric hindrance. That's what those little parenthesis things kind of indicate. You know, it's bumping in. The CN is bumping into the methyl, and it actually kind of prevents reactivity. Okay, and so yes, it's much slower, if it even occurs at all. This is such a significant interaction. This will drastically diminish the reactivity. Okay, so we just say much faster, much slower. The actual exact rate difference is not that crucial. Okay, this is, we also call this a Neopentyl interaction. Neopentyl interaction. You actually you might have, well, you definitely did learn about Neopentyl before. You've probably forgotten about it. Remember this kind of, or actually here. Remember this branched substituent? It's one of the other ones we learned. We learned about isopropyl, secbutyl, isobutyl, tert-butyl, but this is called Neopentyl. Neopentyl, because it's how many carbons? 1, 2, 3, 4, 5. Neopentyl refers to this 5-carbon fragment, Neopentyl. And this sort of arrangement here, if you kind of cut out the ring, it sort of looks like Neopentyl, right? It kind of looks like 1, 2, 3, 4, 5. So there's 5 carbons, and that's Neopentyl. And anyway, so when you hear about people saying that a SN2 reaction is slowed due to a Neopentyl interaction, it basically means you have extensive branching next door to the carbon with the leaving group. Alright, so that's the last topic from Chapter 6. Kind of the idea of a like neighboring branching affecting an SN2 reaction, and this idea of what we call a Neopentyl interaction, which is like extensive branching next door that diminishes reactivity. So it's much slower than like this top example. Okay, so on to Chapter 7. Alright, so now we're on to Chapter 7. Chapter 7, which is a nice title for Chapter 7 is going to be Further Reactions of Haloalkanes. Further Reactions of Haloalkanes. Further reactions of haloalkanes. Particularly, we're going to learn about SN1, E1, and E2. Those are the key reaction mechanisms we'll learn about. So recall, you know, the main things from chapter 6. About the SN2 reaction. Usually put the N a little subscripted. We showed various examples like iodopropane with maybe like Na+, Cl-, maybe DMF, or you know, one of those good SN2 solvents that you could do an SN2 reaction. NaI. Okay. K+, Cn-, DMSO. What's the product of that reaction? It's just another SN2 reaction. Here the chloride kicked off the iodide. Here the Cn kicks off the iodide and makes nitrile. Maybe Ki byproduct. Alright, that's all easy stuff. What about, we could do secondary, remember secondary? 2-bromobutane. We'll do Na plus S. Nice good nucleophile. All the sulfur ones are good nucleophiles. Thiolate. Here this kick this off. This kick that off. This kicks that off. What happens to the stereochemistry of the secondary site? It gets inverted. Make a sulfide, NaBr. What's your favorite SN2 solvent other than DMF and DMSO? Pick one, I don't know, we could say acetone. All of those are good polar aprotic SN2 mediating solvents. Okay, so that's kind of like what we learned about in chapter 6. The mechanism of all these reactions is SN2. What does SN2 stand for? Substitution, nucleophilic, bimolecular. Substitution, nucleophilic, bimolecular. Okay. Alright, so now what's going on with chapter 7, which is sort of these other reactions, SN1, E1, and E2. What's going on with those? Alright. So, number 1 of chapter 7. We're going to talk about something called solvolysis. Solvolysis of tertiary and secondary haloalkanes. Okay, so first we've got to talk about what solvolysis means, and then interestingly this is going to be a reaction that occurs on tertiary and secondary, not primary, not methyl. So that's kind of a difference between the last chapter. Okay, so it's going to be, what's going to be our definition of solvolysis? It's going to be a reaction via substitution. A reaction via substitution with a solvent molecule. What's a solvent molecule? Like above, you know, these are acetone, DMSO, DMF. Those aren't really involved in the mechanism aside from just solvating the nucleophile properly. In this case, substitution with a solvent means that the solvent is going to be causing the substitution. It's going to, the solvent is actually going to be the nucleophile. Okay, that's weird. It's a little different than what we saw before. Examples will be like water, can be a solvent and a nucleophile, methanol, alcohols, water, methanol, ethanol. Those are going to be the kind of things that undergo this solvolysis process. Okay, so a couple examples of solvolysis. We're on solvolysis now. Solvolysis examples. So if we have tertiary bromide, tert-butyl bromide, and we're going to react it with water. So this is not an SN2 reaction. We'll talk about the mechanism in a bit. The byproduct, well, the product is actually going to be tertiary alcohol. And the byproduct is going to be HBr. Okay. And over on the right, I'm going to sneak in relative rate. Relative rate will be on the right. And the relative rate of this one is 100,000. 100,000. It's 1 and 5 zeros. 100,000. Okay? Relative rate is 100,000. Okay, so that'll be relative to something else, which we'll see in a second. Now, if we do secondary bromide, same reaction. This is not an SN2 reaction. It's a different kind of reaction. We get solvolysis to isopropyl alcohol. That's much slower. So the relative rate is 1. So with the tertiary, it is 100,000 times faster than the secondary. Secondary does go, it's just much slower, right? Primary to make ethanol. What do you think? If secondary was extremely slow, what do you think primary is? It's NR, no reaction. It does not go at all, whatsoever. And methyl. To make methanol and HBr. What do you think? Big number, small number, or NR? It's also no reaction. So this reaction only happens for, well, really substantially for tertiary, and secondary it does happen. It's just slower, much slower, 100,000 times slower. Okay, so the big thing is this happens for secondary and tertiary, with tertiary being really fast. Okay. Also, happens with alcohols. So if I have a tertiary chloride and I react with methanol, yeah, it works. What functional group was I getting up top? We're going from a bromide to a alcohol. We're making alcohols. Now we're actually reacting chlorides with alcohols, and we're making ethers. So it's like the oxygen is attacking, but there's more to the mechanism. It's not like SN2. You know, SN2 is like the nucleophile attacks, kicks off the leaving group. That's not what's going to happen. There's more to it. But yeah, generally speaking, this replaces the leaving group, and then you get an ether, right? What about secondary? Think it works? Yeah, it works. This time I'll change to ethanol. Just for fun. And now you get ethyl ether. Methyl ether, ethyl ether, HCl. It does not happen for primary, not for primary or methyl. Just like it didn't happen before for primary and methyl. Okay? We'll just say quickly that with solvolysis, therefore, with solvolysis, the reaction-reactivity order is reversed. The reaction-reactivity order is reversed compared to SN2. the reaction reactivity order is reversed compared to SN2. Meaning, if you're doing SN2 and you had a good, good nucleophiles, methyl was the insanely fast one, primary was a little slower, secondary was a little slower, and then tertiary was just completely not reacting at all. Now it's reversed with this weird Solvolysis reaction we're talking about. Now it's like tertiary is the good one, secondary is kind of bad but works, and then primary and methyl are totally no reaction. In words, with Solvolysis, the reaction reactivity order is reversed compared to SN2. That is absolutely true based on the data that I just provided. Okay. So with Solvolysis, tertiary best, secondary slow but viable, primary and methyl NR. No reaction. No reaction for primary and methyl for the Solvolysis reaction. So, a little bit more about this Solvolysis reaction now, number 2. It's going to have a different mechanism, and we're going to give it a different name. I already mentioned that name a couple times now. It's called unimolecular nucleophilic substitution. Unimolecular nucleophilic substitution, or it's going to be called SN1. A little different than the SN2 reaction from last chapter. And recall, when we considered the rate of the last reaction, the SN2 reaction, recall the rate of the SN2 reaction rate was equal to K, it's a rate constant, times Rx, which is the substrate, times nuke, and that's why we call this bimolecular. SN2 is bimolecular. And it's moles per liter times 1 over seconds, so it's rate, moles per liter divided by seconds. And it was bimolecular, right? For Solvolysis, which will be the SN1 reaction, as an example of the SN1 reaction. For Solvolysis, which is an SN1 reaction, the rate is a rate constant times just the substrate. Moles per liter and 1 over seconds. So it's a little bit different. The nucleophile is not involved in the rate limiting step for Solvolysis, which is an example of an SN1 reaction. Okay, and so you could say varying amount of nucleophile, varying the amount of nucleophile does not affect the rate of the reaction. In the Solvolysis, right? So if I was doing an SN2 reaction and I doubled the amount of substrate, it would double the rate. If I doubled the amount of nucleophile, it would double the rate. Solvolysis, if I double the amount of substrate, it will double the rate, but what happens if I double the amount of nucleophile? No effect at all, right? Because it's not involved in the rate. So that's kind of weird. And that's going to make sense when we consider the mechanism in a few minutes. Alright? Cool. So this suggests a different mechanism. And it is a totally different mechanism. Totally different mechanism. Okay. And the key difference is that there's going to be an initial event in the mechanism that involves just the substrate. Substrate but not nuke. And that's going to be the rate limiting step of the reaction. Okay? So, and that initial event that dictates the entire rate of the reaction. So if the initial event is slow, and it is slow in this case, if the initial event is slow, we have a name for it. It's called the rate limiting step. Or if you're going to abbreviate that, what do you think? RLS. The rate limiting step. Okay? So we're continuing number 2, which is sort of the mechanism of this solvolysis SN1 reaction. Just in general terms, what we just said was that there's kind of like an initial event that just involves a substrate, and then something later involves the nucleophile. How do we draw that in kind of in a manner that sort of explains what's going on? That's a solvolysis substrate, tertiary bromide, really good solvolysis substrate. So something's happening. I'm going to just say slow. We're not sure what it is yet. Well, we do, and I know, but you don't know it yet. Something happens to make something, and that's very slow. Okay, and then the nucleophile comes in, water, as an example. That's very fast. Water comes in, and that's very fast. And then basically some kind of, you get your end product. There might be a little bit more to the mechanism. But the point here, this is the nuke, the water's the nucleophile, is what if you double the amount of nucleophile? Does that speed up the reaction? It doesn't, because there's an initial slow step, and a slow step only involves the nucleophile. Sorry, the substrate. The slow step only involves the substrate, right? The slow step only involves the substrate. So if you double this, then the rate of the overall reaction will double. But if you double the amount of nucleophile, well, that's on the fast step after the initial slow step. So doubling this won't have any effect on the reaction rate, the overall reaction rate, because the overall reaction rate is kind of dependent on the first step. What's another way to consider that? It's like a bottleneck. Like this is the bottleneck. This dictates the overall rate of the reaction. It's called a bottleneck. This is the RLS. RLS, which is the rate limiting step. Okay. I think there's a figure in the book, figure 7.1, that sort of shows that visually. I'm pretty sure it's figure 7.1. You can take a look at that. Okay, so the observed rate is the rate of the slowest step. That's a general phenomenon. If you have an initial slow step, which this is an initial slow step, the observed rate is the rate of the slowest step. Okay? Alright. The mechanism is called SN1, and we'll go through it in detail coming up, I think, the next lecture, really. Substitution, nucleophilic, unimolecular, meaning that the rate only depends on one substrate. Okay? I'm gonna, in the last second, just kind of overview the mechanism, because it's really not that bad, and then we'll go through it in very excruciating detail next time. So I'll do it real quick. This won't be a quizzable item. Yeah, but I just want to kind of mention it, just, for the motivated students. You'll be kind of psyched to see it. It's not that bad. All right. So if we're reacting tertiary bromide with water to make tertiary alcohol and HBr. The key things are that this is going to go away. The leaving group goes away. So it kind of falls off initially. The leaving group falls off initially. It's not like the nucleophile kicks it off the way that it did in the SN2 reaction. And now you get this weird thing called a carbocation. Remember carbocation? We've talked about that a few times. It's a positively charged thing. Okay? This is a slow step. It doesn't really want to fall off, but it does, and it doesn't involve the nucleophile. Okay? Then the water comes in, and then that's when the nucleophile actually attacks at the carbocation stage. We're still not done, actually. This is a couple-step mechanism, right? Water attacked and forms this sort of oxygen-carbon bond, plus charge here, and then Br minus, which you have, takes off the proton, and that gives you the HBr. Isn't that cool? It's not that bad. It's not that bad. The mechanisms get crazier and crazier through the course, but this is a summary of the entire mechanism of solvolysis. We're going to go through this all in detail next time. Alright, I'll stop here, and yeah, so more detailed next time on the solvolysis mechanism, each of the steps, the energetics, and all that kind of stuff. All right.